In this video, we're going to talk about how we know what we know about atomic structure today. And we're going to take a step back to Dalton's atomic theory, which is in the early 1800s, where he came up with the billiard ball model of the atom. Basically, his idea was that at some point, matter is going to get so small that it becomes indivisible, and through experimentation, he was able to show that different elements combined in different ratios, and there were a few laws involved, including the law of conservation of mass, law of multiple proportions, and law of definite composition that helped drive his atomic theory, but he didn't know any more detail than that. He didn't know about any of the subatomic particles that we know about today. So the first subatomic particle that was discovered through J.J. Thomson's cathode ray tube experiments, and it led to the plum pudding model of the atom, which you see here. So they still didn't know about the nucleus, but what he did is essentially he had a very diffuse gas in a tube, and when he ran an electric current through it, it essentially made a beam that went across the tube. And they recognized that that beam was able to be deflected by electric and magnetic fields, and they were able to determine that there was this negatively charged component that existed for all atoms. So no matter what gas they used or what metals they used using the electrodes, they were able to get electrons from them. So they became a core component of what we know as the atom, but they didn't know about the nucleus. And J.J. Thomson's model, again called the plum pudding model, this is in the early 1900s. And then Rutherford set forth to prove that that model was correct. And to do so, he had a thin sheet of gold foil, and he was firing alpha particles at it, which are 2 protons and 2 neutrons, basically a helium nucleus, at this really thin sheet of gold foil. And based on the atom being like this, he thought those particles would go straight through, and their path would pretty much not be impeded at all. But then what happened when he did the experiment was that most went straight through, like he predicted, but some deflected back at really large angles, and that led him to believe that there was a dense positive center in the atom that we now know as the nucleus. So these are our early atomic models that existed before we got to quantum theory. And so the next step along that way required us to use light to start gaining more insight into the atom. So first I just want to talk about what light is. Light is you can think of it as a bundle of energy that has wave-like properties, but for a while, they thought that light was exclusively a wave. And we got that idea because Young's double slit experiment showed that if you shine light through 2 slits in a piece of paper, what you end up with is a pattern of constructive and destructive interference that says light definitely acts like a wave. And then Einstein came along and performed the photoelectric effect where it showed that light definitely comes as a particle in discrete chunks. Okay, and he did this in the photoelectric effect real quick. If you have the same amount of energy being shined on a piece of metal that's from red light, so you can see the intensity is at 100% with 700 nanometers, or 350 nanometers at 50%, those lights would both be transmitting the same amount of energy. But you get different results in that only the shorter wavelength or the higher frequency photons would be able to eject the electrons. And that gave us the idea that the energy in light comes in discrete little bundles of energy that we call photons instead of being a continuous wave. So we can use the properties of light to take a deeper look into the structure of the atom. And that's what Niels Bohr did in coming up with his model of the atom in 1913. And I'm going to go to a simulation to show you in a little bit better of a fashion how this actually works. And in addition to the work performed by Max Planck, who basically showed the relationship between the frequency of a photon and the energy possessed by it was a direct relationship. We use Planck's constant for that. You could say that by looking at what happens when you heat a gas and you add energy to it, you can look at what the energy coming out from it is, and that can tell us about the structure. So in Bohr's model of the atom, he basically, if you took hydrogen and you put it in a gas tube, what you would see coming out of it is only specific wavelengths of light. And what that means is that the atom can really only lose specific amounts of energy or gain specific amounts of energy. And so what happens when an atom of hydrogen does this, and this goes for all atoms, but his calculations only really work for hydrogen, is when the electron absorbs energy, it jumps from, right now it's falling down slowly. When it absorbs energy, it jumps from a ground state to an excited state. And it does it all at once. It does a quantum leap. So the energy is absorbed all at once, and then as it falls back down to lower energy states and eventually the ground states, it also releases that energy only in discrete chunks. The electrons can't exist between energy levels. They can only exist in these orbits. Didn't really have a good idea as to why, but it's what happened. And so it led to the idea that if the electron could exist anywhere in between the nucleus and the outer edge of the atom, it could gain or lose any amount. And you would get a continuous spectrum, or basically the whole rainbow emitted by the atoms. But that's not what we see. We only see specific line emission spectra. So only these wavelengths of light are given off. And based on what we can see, those are the amounts of energy that can be gained or lost by the atom. So we know the atom has discrete energy levels. And then following his work, de Broglie added on to that a little bit. He came up and he combined Einstein's equation, E equals mc squared, as well as Planck's equation that energy is equal to the Planck's constant times the frequency, and combined them to get to the point where we could say that everything that's moving has a wavelength to it. And for really small things like electrons, it's actually better to think of them as a wave. And you can actually see that from an electron diffraction pattern and an X-ray diffraction pattern, their wavelengths of the movement are about the same, okay? And what this looks like in live speed is that in de Broglie's model of the atom, the electron essentially is viewed as a wave and not a particle, okay? And there are only a set number of nodes that can exist in a standing wave, so this explains why you have only these specific orbits, okay? So then following that, more work was done by Erwin Schrödinger and Heisenberg. And their work showed that, so Heisenberg came up with the uncertainty principle. And basically, the more you know about the position of an electron, the less you know about its movement. And at some point, if you're trying to define this position of an electron, it becomes really difficult, and it's better to view their locations as probability functions. Essentially, the electron is somewhere in this area, okay? And combining that with Schrödinger's wave equations, we were able to come up with a solution that basically gives us modern atomic structure or orbital structure. It gave us the different subshells that we see, the S subshell, P subshell, D subshell, the F subshell, that we now use in electron configuration, which really defines where elements can be found on the periodic table today. Which is really interesting because Mendeleev came up with the periodic table in the middle of the 1800s before an electron was even discovered. He arranged everything based on the properties of the elements. However, it turns out the properties of the elements are a result of the electron arrangement, which was described by Schrödinger.